Hello everyone. In this video we are going to talk about polynomial regression, which is basically it is a linear regression, but the function we are trying to fit in general in terms of the input variable, it is a polynomial, but in terms of the unknown parameters, it is still a linear function, right? So let's say, for example, you have basically some function like y equals like a or c naught, let's say, plus c1 times, right, x squared, correct, and then plus c2 times x, and then the other one times x squared, right? So you have some function like this. So clearly, in terms of the input, you see it's nonlinear function, but in terms of the unknown c0, c1, and c2 is still linear, so I can still use my linear regression. The only thing is, what I need to do, I can define this as c0 times 1 plus c1 times x plus c2 times x squared, and then so now if I, for each data x, if I define this number, this one, and this one as a vector, and then I can treat this as what? As a linear regression. So I can say this is equals to what? C0 and C1 and C2, right? A dot product with vector that is x to the power 0, x to the power 1, and let's use power as Python, and x to the power 2. Correct? So I can use it as a dot product or a transpose, right? And then this is clearly a linear regression. The only thing is to form this vector for each data x, and that we use using something from the Scikit Learn called polynomial features. So in order to do this, we need two things from the Scikit Learn. From Scikit Learn pre-processing, we need these polynomial features. So when we create this vector for each x, this is a part of pre-processing. So we bring it from Scikit Learn pre-processing, and again, the function is called polynomial features. And then from the Scikit Learn linear model, we bring in the linear regression, which we're going to use to calculate these three parameters. We also need pyplotlib, and we need numpy. So here I have 5 data points, x and y, and there is a quadratic relation between them. I know it ahead of time. Now, in reality, you don't, so you have to try, but here I know, just for the sake of experiment, plus some random addition or subtraction. And then what I did is I brought my linear regression object and defined it as reg. Then what I need is I need to pre-process my x's and generate these vectors. So first, I say I want polynomial features, and then I pass the degree. So here I use degree 2. Then I say now go ahead and apply this quad featurizer object, the method called fit_transform, and apply x to it. Apply it on x, I'm sorry. And the output, call it x, xt, or x of training data. Now, if I show you this x of training data, you see for numbers 2, 3, 4, 5, 6, for each one, there is such vector. Okay, let me show you that right now before I do any regression. So this pre-processing part I show you. You see? 2 to the 0, 2 to the 1, 2 to the 2, all the way, 3 to the 1, 3 to the 0, 1, 2, all the way to 6. So this here, each row of that, along with one of these y's, is what I pass to my linear regression function next, and that is going to give me all the coefficients. So this is my next part now. Now I have my linear regression object, call it reg, and I say reg.fit to what? To the x of training, which is now in this format, and the y of training, which are this data. Now that is going to fit the object, and when it does that, now I can see the coefficients of the fitted polynomial, as well as this r squared coefficient, which is the closer it is to 1 means a better fit I have. So if you want, I can show you these numbers without any plot at the moment, and then we can do further plots. So let's look at this number as well. Okay, so you see now the coefficients are what? This is for C0, this is for C1, this is for C2, and then this number is very high, 0.997, of course, because the amount of randomness in these numbers are not huge, as we'll see on the plot. Now, I want to test my function on some new data. So here I create some new data, a lot more than the original one. So between 2 and 6, which is the minimum and the maximum, I create 20 points. And then the important thing is when you generate it with linear space, before you pass it to this polynomial features and transform it to this matrix format, what you need to do, because you did not start it as a NumPy array like this, you use the linear space command. The first thing is you first use the reshape of -1 and 1, okay, then pass it to the fit transform. Otherwise, you're going to get an error here. So you have to do this reshaping, then pass it to the transform, and then what you can do to know which values of y it gives you, this function, this polynomial with these coefficients, it gives you for those x values, use the reg.predict, right? You know, predict gives the output for a fitted function, for a fitted regressor, a regression function. And so you pass these and you get 20 data points, and then I'm going to show you with these 20 data points a function, right, that I use for my test points, and I show you with the scatter plot my original 5 points all on the top of each other. So let me show you that. There we go. So I use 20 points here, and you show this kind of underlying function that is fitted, and these are my 5 points. As you see, they are not far off from the curve, and that's why this number is high. Now you might ask me, what happens if my function is not a polynomial? If it is a polynomial higher order, you just change this degree. But if it's not a polynomial, then what? Can I still use the linear regression? Yes, as long as in terms of your unknown parameters, it is a what? It is a linear function, you're good. For example, if your function is something like y equals, let's say, a times log or natural log of, let's say, b times x, right? This is clearly nonlinear in terms of x and a and b, because there is natural log of b, right? Or exponential. Let's use exponential, that's better, right? Something like that. Now, what I can do is convert it into linear. So I take natural log from both sides. So it's going to be natural log of y equals what? Natural log of a, and then plus b times x, right? If I take natural log. Now, if you look, I can say this is natural log of a and b dot product with what? With 1 and x. And again, it could be x to the power 0 and x to the power 1, right? Because x to the power 0 is 1, and here I can say natural log of a times 1. So now if I call this natural log of a another parameter, whatever you want to call it, a prime or something, whatever, now in terms of this one and this one, clearly the system is what? A linear, as long as instead of y, I use natural log of y. Okay, so you have to take natural log from your y data. For your x data, you use this polynomial feature with power 1, or since it's linear regression, you don't even need to do that. And then that is going to give you these two parameters. Once you have b, then you know AP is equal to what? Equals to natural log of a, and from here you can say a is what? A is exponential of A prime, right? So you get your A from here and you get your B. So you can, as long as you form the data properly, you can do it with any function as long as you can write the relation between y and x as a linear function in terms of the unknown what parameters. So there are many other functions that you can write it this way. So this is how you go about polynomials and a little bit more complicated. Hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.